Dear viewers and listeners, I welcome you all to another episode of our weekly online chemistry class. This is season 7, episode 2. In the previous episode, we talked about ionization energy, the trend of ionization energy in the periodic table, both across the period and down the group. We also discussed some exceptions to the general trend in ionization energy of elements in the periodic table. And likewise, do not forget, we have discussed in details Slater's rule and how to determine effective atomic number of elements under season 6, episode 4. In today's episode, we are going to base our discussions on electron affinity, which is the second periodic property of elements. Electron affinity, EA. Electron affinity, by definition, is the energy released either in kilojoules per mole or in electron volts per atom when an electron is added to an atom in gaseous state to produce a gaseous anion. In a nutshell, electron affinity can be represented assuming you have an element X in gaseous state and you are adding an electron to that element to produce the anion of that element in gaseous state. The energy released in this process, enthalpy change of reaction, is equal to what we refer to as electron affinity, and it is always negative in value, meaning energy is released whenever electron is added to an atom in its neutral state. However, the variations of electron affinity in the periodic table is dependent on two factors. But generally, electron affinity increases across the period from left to right in the periodic table and decreases down the group from top to bottom as well in the periodic table. And these trends are dependent on two factors, as I mentioned earlier. Those factors are the size of atom, what you also refer to as atomic size, and the other factor is nuclear charge. So how does the size of an atom affect electron affinity of that particular atom or element? We know that as the size of atom increases, especially down the group, when you go from top to bottom down a particular group in the periodic table, there is increase in size, and that is as a result of increase in the number of shells. Take for instance, if you look at group 1 element, we have lithium, we have sodium, we have potassium, we have rubidium, among others. Lithium atomic number 3, 11, 19, and so this is 281. I mean, this is 21, this is 281, this is 2881, this is 2881. So you can see that as you go down the group, and if you add these together, 26, 36, that will give you 37, which is the atomic number of rubidium. So you can observe that as you are going down the group, there is increase in the number of shells. Lithium has 2 shells, while sodium has 3 electronic shells, 4 for potassium, and so on and so forth. So the size of the atom gets increased from time to as you go down the group. So this increase in size reduces the electrostatic force of attraction between the positively charged nucleus of that atom and the valence electrons. And as a result of that, it becomes more difficult to add electrons to such atom. So as you go down the group, when you are trying to add electrons, you need more energy because the position of where the electron to be added is not energetically favorable. So you need more energy to add electron to an atom as you go down the group. And in that case, less energy is released. And the amount of energy released in the process is what is measured as electron affinity. Although electron affinity is difficult to measure directly as compared to ionization energy. But we normally measure that from what we call Born-Haber cycle using S law. We are going to discuss that when we start, by the time we look at the thermochemistry under physical chemistry. This is the method from which you can determine or measure the electron affinity of an atom. So as you go down the group, there is increase in size, and that increase in size causes a reduction in the electron affinity value of element, although there are some exceptions to that. Now, nuclear charge. We know that as we go from left to right across a particular period in the periodic table, there is increase in atomic number, and likewise there is increase in the valence shell electrons, because electron is being added to the same shell. So as a result of that, nuclear charge increases. And the increase in nuclear charge also causes an increase in the electrostatic force of attraction between that positively charged nucleus and the valence electrons. If you take period 2, for instance, where we have lithium, beryllium, boron, carbon, nitrogen as an instance. Lithium 3, 4, 5, 6, 7. This is 2, 1, 2, 2, 2, 3, 2, 4, 2, 5. You can observe that all the atoms have 2, 2 shells because they belong to period 2. But the number of electrons in the atomos shells increases in that order. Likewise, their atomic number also increases from 3 to 7. So that increase in atomic number and effective nuclear charge reduce the size of the atom. And as a result of that, it becomes more favorable to add electron to such atom as you go from left to right in general terms in the periodic table. So therefore, what this implies is that from left to right, generally electron affinity increases with increase in effective nuclear charge as a result of what we refer to as increase in effective nuclear charge. So as a result of this, I want us to look at some of the exceptions to this general rule in terms of electron affinity. One, there are some questions that need to be answered. The first is that one should be able to explain why the electron affinity of period 2 elements are higher than that of period 1. That's a very, because we believe that electron affinity increases down the group, but that general term is only applicable to group 1 element, whereby from lithium to francium, electron affinity decreases. But when you get to group 2, we discover that electron affinity varies somehow. It increases and it decreases. The same thing applies, and a typical example of that is that we should be able to explain why fluorine has less electron affinity than chlorine, and why oxygen has less electron affinity than sulfur. If you go to that period, or in particular group 7 or 17, you observe that fluorine is the first member, while chlorine comes under after fluorine. Sulfur is also below oxygen. So we expect fluorine to have higher electron affinity than chlorine, and we also expect oxygen to have higher electron affinity than sulfur, since we said earlier on that electron affinity decreases down the group. But the reverse is the case, and students of chemistry are expected to be able to give us reasons for these observations. And the reason is not far-fetched. You observe that when you are adding electron to fluorine, oxygen, or nitrogen, you are adding an electron to the compact 2p orbitals. Because in fluorine, the electronic configuration is 7, 8. You have 1s2, 2s2, 2p5. For oxygen, you have 1s2, 2s2, 2p4. So in this case, you will observe that when oxygen gains an electron, the electron will go to the 2p orbitals. When fluorine also gains an electron, the electron will also go to the 2p orbitals. And adding electron to this atom makes or causes an increase in electron density because of the compatibility of the 2p orbitals of the two atoms. And that is as a result of the smaller sizes of fluorine and oxygen compared to chlorine and sulfur. We know that chlorine and sulfur are bigger in sizes than fluorine and oxygen. So as a result of that compatibility and higher electron density, it makes it difficult to add electron to fluorine and oxygen. So adding electrons to these two elements releases lesser energy compared to adding electrons to chlorine and sulfur. And this is the main reason why chlorine and sulfur have higher electron affinity than fluorine and oxygen respectively. The same thing can be said of nitrogen and phosphorus, because the electron affinity of phosphorus has been observed to be higher than that of nitrogen. The same explanation can be said of this, because when you are adding electron to phosphorus, the electron enter the 3p orbitals, which is energetically more favorable as a result of the higher size of the atom compared to nitrogen, where addition of electron enters the 2p orbitals of higher compatibility and resulting to increase in electron density. Another observation that one need to explain is that we must be able to give reasons why alkali metals have higher electron affinity than group 2 elements, which are alkaline earth metals. Why? Take for instance, if you look at lithium and beryllium, lithium atomic number 3, beryllium atomic number 4. Beryllium is in group 2, lithium is in group 1. The electronic configuration of lithium is 1s2, 2s1, while beryllium is 1s2, 2s2. So meaning electronic configuration of an atom is also another factor that may affect its electron affinity. If you look at this, the 2s orbital takes maximum of 2 electrons. In lithium, that 2s orbital has 1 electron, meaning it can accept 1 more to complete this shell. But in beryllium, this 2s orbital is completely filled. So meaning if you are adding another electron to beryllium, the electron will enter 2p, which is empty. And that might not be energetically more favorable, because this p orbital, after adding electron to beryllium, will contain 1 electron, and that p orbital degenerates into 3. And that may not obey unscrew. So in that case, adding electron to lithium will be more favorable, because lithium requires 1 more electron in the 2s orbital, which is in the valence orbital, to be complete compared to beryllium. And that is why lithium releases more energy when electron is added to it compared to beryllium. The same thing can be said of potassium and calcium. And the same thing can be said of sodium and magnesium. The same explanation. So this is another observation that students need to take note of when they are looking at variations or in the trends in electron affinity of elements. Another observation, we observe that the electron affinity of alkaline earth metals, that is the group 2 element, where we have beryllium, magnesium, calcium, strontium, barium, and radium. These are the members of group 2. We discovered that their electron affinities are almost tending towards 0. Why? Meaning the value is around 0 approximately. And what result to that is as a result of their stability in the valence orbital electronic configuration of NS. Their valence electrons is found in the NS, and that s orbital is completely filled, which can take maximum of 2 electrons. That is the reason why these members of that group have almost 0 electron affinity. Another observation is that adding electron, we observe that the electron affinity of nitrogen is lower than that of oxygen, despite that both of them are members of the same period. Why? Students must be able to explain this. And that is down to the electronic configurations of the 2 atoms. The electronic configuration of nitrogen is 1s2, 2s2, 2p3. This p orbital degenerates into 3, and each one of them takes 1 electron in accordance to Ohm's rule. In oxygen, with atomic number 8, we have 1s2, 2s2, 2p4. That p orbital again degenerates into 3. This takes 2. The other p orbitals take 1. And I said in the previous episode that a half-filled orbital or empty orbital or completely filled orbital is stable compared to partially filled orbital. In nitrogen, the 3p orbitals are partially filled, which has an extra energy of stability, compared to oxygen, where one of the 3p orbitals is completely filled and the other 2 are empty. So this is not as stable as compared to this. So adding additional electron to nitrogen requires more energy due to that p orbital extra stability. So in that case, lower energy will be released when electron is added to nitrogen in neutral atom, the neutral atom of nitrogen, compared to the neutral atom of oxygen, which has less stability compared to nitrogen atom. So these are the observations that students must take care note of. Another interesting thing, which will be the last on electron affinity, is that students should know that the second electron affinity of an atom is always higher than that of the first. And as a result of that, meaning it is more positive than the first electron affinity. And what accounts to that? When you have oxygen atom in neutral state, add electron to it, you have oxygen mononegative ion. So this is the first electron affinity, which is negative in value. If you are adding electron, an additional electron to that ion, you are going to get 2 minus, which is EA2. So we discover that this one is higher than this. Why? Because after adding the first electron to oxygen in its neutral state, the atom has now been ionized. So the extra electron repulsion between the electron that are already been added and the newly added electron causes the atom to have higher electron affinity. So in general, the second electron affinity of an element is always higher than the first. I believe with this, you must have learned 1 or 2 things on electron affinity, and students must be able to answer some pertinent questions that are raised during the discussions. You must be able to define the term, you must be able to tell us the general trend both across the period and down the groups and what factors are responsible for that, and you must be able to tell us some of the exceptions to those general trends of electron affinity in the periodic table of elements. Do not forget to click on the subscribe button whenever you are watching our video. Thanks for listening. See you again some other time.